80 megahertz, 2.5 terawatts pulse peak at 430 megahertz, and 300 megawatts at 47 megahertz. The European Incoherent Scatter Scientific Association, or ISCAT for short, operates an ionospheric heating facility capable of transmitting over 1 gigawatt effective radiated power (E.A.R.P.) near Tromsø in Norway. It operates 3 incoherent scatter radar systems at 224 MHz, 931 MHz in northern Scandinavia, and 1 at 500 MHz on Svalbard. Russia has the Sura ionospheric heating facility in Vasilsursk near Nizhny Novgorod, capable of transmitting 190 megawatts E.A.R.P. from 4.5 to 9.3 megahertz. The facility consists of 3 250 kilowatt broadcasting transmitters and a 144 crossed dipole antenna array with dimensions of 300 meters by 300 meters. At the middle of the operating frequency range, 4.5 to 9.3 megahertz, a maximum zenith gain of about 260 is reached. H.A.A.R.P high-pass observatory, capable of generating 70 megawatts E.A.R.P. at either 2.85 megahertz or 4.53 megahertz, is northeast of Fairbanks, Alaska, and operated by the UCLA Plasma Physics Laboratory. The fifth is H.A.A.R.P, producing 4 gigawatts E.A.R.P. north of Gacona, Alaska. H.A.A.R.P is an ionospheric research program jointly funded by the U.S. Air Force, the U.S. Navy, the University of Alaska, and the Defense Advanced Research Projects Agency, DARPA. The most prominent instrument at the H.A.A.R.P station is the Ionospheric Research Instrument, IRI, a high-power radio frequency transmitter facility operating in the high-frequency HF band. The IRI is used to temporarily excite a limited area of the ionosphere. Other instruments such as a VHF and a UHF radar, a fluxgate magnometer, a digisonde, and an induction magnometer are used to study the physical processes that occur in the excited region. Part 2. H.A.A.R.P's Prehistory. Most believe that, although admittedly inspired by the wireless power transmission patents of Nikola Tesla, the original designs for any kind of atmospheric heating device do not date back any earlier than January 10, 1985, with patent number 4,686,605, applied for by Spring, Texas inventor Bernard J. Eastland. Thus, in discussing H.A.A.R.P, it is usually the Eastland patents that are considered first. But the prehistory of modern ionospheric heaters begins with the United States Central Intelligence Agency, U.S. CIA, developing a program called MK-Ultra to find a reliable truth serum that could replace the placebo sodium pentothal. MK-Ultra tested a variety of chemicals on unknowing subjects in mental asylums, prisons, the armed forces, and eventually even students on U.S. college campuses. It was at that point that one of MK-Ultra's test chemicals, LSD-25, became the dominantly popular drug in the U.S. youth culture. However, by the so-called Summer of Love in 1967, The Soviet equivalent of the US CIA, the KGB, had long been developing its own equivalent programs to the CIA's MK-Ultra. Behind the Iron Curtain, research into the field that the CIA had long dubbed MK for mind control was conducted as experiments testing for parapsychological abilities such as extrasensory perception, ESP, telekinesis, TK, pyrokinesis, PK, clairvoyance, prophecy, etc. This field has since been dubbed psi research. Nina Kulagina displayed remarkable psychic abilities, including telekinesis and psychokinesis. In 1968, her films were shown at the first Moscow International Conference on Parapsychology. In this footage, she appears to be moving metal objects solely by moving her hands above them. This effect, if real, is clearly magnetic in nature and, as we see here, can result in wild rotation of a compass needle. Contemporary to their research into psi and related phenomenon, the Soviet Russians were also testing over-the-horizon (OTH) radar systems using enormous antennae arrays. The first experimental system, Duga-1, was built outside Mykolaiv in Ukraine, successfully detecting rocket launchers from Baikonur Cosmodrome at 2,500 kilometers. This was followed by the prototype Duga-2, built on the same site, which was able to track launches from the Far East and submarines in the Pacific Ocean as the missiles flew toward Novaya Zemlya. Both of these radar systems were aimed east and were fairly low power, but with the concept proven, work began on an operational system. The Duga-3 systems used a transmitter and receivers separated by about 60 kilometers. The Duga-3 array went online around July 1976. The result was the worldwide Russian woodpecker radio signal. The woodpecker signal had an interpulse period of about 90 milliseconds, a frequency range of 7 to 19 megahertz, a bandwidth of 0.02 to 0.8 megahertz, and typical transmission time of 7 minutes. The signal was observed using 3 repetition rates: 10 Hz, 16 Hz, and 20 Hz. The most common rate was 10 Hz, while the 16 Hz and 20 Hz modes were rather rare. The pulses transmitted had a wide bandwidth, typically 40 kHz. This signal was continually broadcast until December 1989. According to some reports, the Komsomolsk na Amur installation in Siberia was taken off combat alert duty in November 1989. The original Duga-3 site lies within the 30-kilometer zone of alienation around the Chernobyl power plant, which suffered a nuclear reactor core meltdown on April 26, 1986. The woodpecker signal was considered aggressive by US and NATO during the Cold War because it bordered on interference with worldwide radio transmissions. Part 3. The ionosphere. To begin, we will be looking at a certain portion of the spectrum of electromagnetic radiation. On this chart we see Y-class, called gamma radiation at the top, is extremely high frequency, extremely short wavelength radiation with high energy. Gamma rays are capable of dissociation of atomic nuclei, meaning a laser of this kind of radiation would fire a beam that could split an atom and ignite a nuclear fission reaction, alike an atomic bomb. Below gamma rays are X-rays, and below X-rays ultraviolet light. At the level of ultraviolet radiation is where we see the photoelectric effect occurring, with photons being absorbed and re-emitted by electrons, resulting in the wavelengths of the next level lower on the scale of radiation by energy levels, the visible spectrum. Below the frequency per wavelength of visible light rays, we encounter infrared radiation, and below this, of slower frequency and longer wavelength, is radio wave radiation. Radio waves result in an effect of physics called plasma oscillation inside metal antennae. Radio wave frequencies range from 3000 GHz to 3 Hz, and are of special importance to human sciences because only radiation below 300 GHz remains trapped inside our atmosphere, held there by a layer of ionized plasma called the ionosphere, at a height of about 50 to 1,000 kilometers above sea level. The ionosphere is formed as solar radiation, photons, combine with the gases of the uppermost atmosphere to form an ionized plasma. An ionized plasma is, basically, a gas cloud that has an electrical charge and can thus be influenced by magnetic fields. The ionization of this cloud is what results in the opacity of the atmosphere to slower frequency, longer wavelength radio wavelengths, causing them to become trapped within Earth's geomagnetic field. In short, the ionosphere allows only certain spectrums of biological, non-harmful radiation to reach Earth, as well as prevents a certain amount of magnetically affected radiation from leaving. Although the F1 layer of the ionosphere, responsible for radio wave refraction, is present both day and night, because most of the ionization of atmospheric gas